Hello and welcome to this lesson on binding energy, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson we're going to look at how you can describe binding energy. So if we've been successful and learnt in today's lesson, we should be able to describe the nuclear processes of releasing energy, calculate the binding energy of a nuclear process, and define and describe the concept of binding energy. So we're going to be looking at the following part of the AQA A-level physics specification for nuclear physics and radioactivity, 3.8.1.6 mass and energy. So in previous lessons we've considered the concept of the nucleus in physics. So in our work with the nucleus, we assume that the nucleus is a perfect sphere and a point charge. These two assumptions are incompatible, but it's the only way to make the mathematical equations compatible. Now Rutherford estimated the distance of the nuclear radius by looking at the distance at which the alpha particle gets to the nucleus before stopping, the distance of closest approach. So Rutherford suggested that the kinetic energy of the alpha particle turn into electrical potential energy between the alpha particle and the nucleus, and this is given by the equation R is equal to Q1 Q2 over 4 pi epsilon 0 times by the kinetic energy. Now this value was decided to be an overestimation from the true value because it includes not only the nuclear radius but the separation between the alpha particle and the nucleus itself. Now the true value of the nuclear radius was calculated in the electron scattering experiment, where the de Broglie wavelength of an electron is equivalent to the gap size between the nuclei, and it caused electrons when fired at nuclei to diffract through the substance. Now the equation for the nuclear radius in this instance was given by the equation 0.61 lambda over sine theta, where theta is the minimum angle of diffraction. Now another method to calculate the nuclear radius came from the atomic mass, where we said the nuclear radius is equal to R0 a to the power of a third, where a is the atomic mass and R0 is the average radius of a nucleon in the nucleus. Now if we assume the nucleus is a perfect sphere, then we can calculate its nuclear density, and we said that the density is equal to U over 3 over 4 pi R0 cubed, and all of these values are constant, which means that the nuclear density is constant for all nuclei, which when we give values is about 3.4 times 10 to the 17 kilograms per meter cubed, which is much larger than the atomic density. But there's another equation that we can consider when looking at the nucleus in physics, and that's an equation that links the exchange of rest mass and potential energy in the universe, because mass can be considered a potential store of energy in the universe. So when a particle and its corresponding antiparticle meet, they annihilate with each other. Their rest masses turn into energy in the form of two photons, each with the energy linked to mc squared. Now on the other way around, a single photon of energy in excess of 2 mc squared can produce a particle and its antiparticle, each of rest mass m, in pair production. Now this is important because Albert Einstein published this idea in the special theory of relativity, where he showed that time moves slower the faster you travel, the mass of an object is dependent on its speed, objects shrink when they travel faster, and the speed of light is the only true constant in the universe. But the part of the special theory of relativity we're concerned about in today's lesson is that Einstein used the equation E equals mc squared to show that the rest mass of an object increases when it gains energy and the rest mass of an object decreases when it loses energy. There's a fundamental link between the rest mass of a substance and the energy it possesses. So we could say that the rest mass and the energy were equivalent to each other in an object. So Einstein realized that the mass increase is equivalent to an energy increase in an object, and he also realized that the mass decrease is equivalent to an energy decrease in the object, which we symbolize with the delta notation in this particular equation. Now this equation applies to all energy changes in the universe. However, it's only truly noticeable on the nuclear scale when we look at events such as gamma emission and nuclear fission. So the effect of this energy and mass interchanging must always be considered in the microscopic world of the nucleus and in nuclear decays. So in all nuclear decays, you've got to be able to calculate the mass change in a nucleus from a decay, or the energy given out in a decay, because if the law if we have the law of energy mass conservation, we would say that energy mass before is equal to energy mass after. So in all nuclear decays, you're going to have to think about what happens when you go from your unstable nucleus to your stable nucleus. So you tend to find that your unstable nucleus has a higher mass than your more stable nucleus. So this mass loss is lost as decay energy in the process, which we can also call the mass defect as well. So this increases the stability of the nucleus as it has less potential stored in its actual structure because it has less mass, which is actually why the universe tends to smaller nuclei as they contain less potential energy and therefore are more stable. Now it's important to note that the decay energy is not the radiation particle emitted. This will count as the mass afterwards. It's literally the energy of the emission as well. So if there was only mass found in the universe, we would say that the nucleus before would equal the nucleus after plus the alpha particle in this particular example. However, in reality, it's that the mass before, the nucleus before, has a greater mass than the nucleus after and the alpha particle afterwards, because some of the mass before has turned into decay energy. So the true equation is actually saying that the mass energy of the nucleus before is equal to the mass of the nucleus afterwards plus the mass of the alpha particle afterwards plus the decay energy afterwards. So some of the mass before has turned into decay energy. So some of the mass has been lost to energy, so this mass change is called the mass defect. So we can calculate the amount of energy released in nuclear decays using Albert Einstein's famous equation, E equals mc squared, which gives us the universal relationship between the potential energy stored in an object and its rest mass. So for example, if a piece of material of mass 5 kilograms could be completely converted into energy, how much energy would be released? So we would say E equals mc squared. Okay, and we can get our answer in this case to be 4.5 times 10 to the 17 joules. Now that is a colossal amount of energy, 3 times the amount of energy that arrives at the Earth from the Sun every second. So it indicates just how big a potential energy store mass is. But that's very, very unlikely to have all of the mass of an object change completely into energy. It's more likely a small amount of mass would change into energy. So if a piece of material of mass 5 kilograms lost 0.00030 kilograms of mass during a process, how much energy would be released? So we use here the mass change in our equation, E equals mc squared, and we get our answer to be 2.7 times 10 to the 13 joules. So you always really think about, in terms of nuclear decays, the actual mass change that's taken place. Now you'll notice in our equation, okay, that on the scale of nuclear decays, the unit of the kilogram tends to be too large. So actually when we're looking at mass change on the nuclear scale, we don't tend to use kilograms, we use another unit which we then convert back into kilograms when we use our equation E equals mc squared. So in many examples of nuclear decay, the mass of an atom will not be expressed in kilograms, but rather in atomic mass units. So the mass of an atom is expressed in these atomic mass units U to avoid very, very tiny fractions of kilograms being used. Now the definition of one atomic mass unit is that it is equal to 1/12 of the mass of a carbon-12 atom. Now 1 U is equal to 1.66 times 10 to the minus 27 kilograms. So here are some examples of the masses of the constituent particles of an atom, okay, in these values of U. So a proton is 1.0073 U, a neutron 1.0087 U, and an electron is 5.49 times 10 to the minus 4 U. Now physicists, when they had this idea of E equals mc squared, considered the following problem. If rest mass and energy are equivalents, well then how much energy will be required to remove a nucleon from a nucleus? Now to consider these ideas, we've got to work backwards, because why do nuclei exist in the first place in the universe? And because a nucleus is much more common than free protons or free neutrons, well, why is this? Well, in a nucleus, there's a strong force produced by all nucleons, which is attractive and holds the nucleus together. The protons repel each other due to electrostatic repulsions, but the nucleons come together because the strong force is larger than the electrostatic repulsion, which gives a stable nucleus. So suppose all the nucleons in a nucleus were separated from each other, removing each one from the nucleus in turn, one after the other. Well, work would therefore need to be done to overcome the attractive strong nuclear force and separate the nucleons out from each other. So this tells us that the potential energy of each nucleon is therefore increased when we remove it from the nucleus, because we're putting energy into that nucleon to pull it out of the nucleus. So this stops the nucleons from collapsing back into the nucleus under this attractive strong force. So because now these nucleons, when they're removed from the nucleus, have slightly more potential energy, it means that their mass will increase slightly, E equals mc squared, but it also means that they're slightly less stable. So this means that the lower energy state is found in the nucleus, so therefore actually our nucleons have less energy whilst in the nucleus and are therefore more stable. So when the nucleus is separated into individual nucleons, the individual nucleons all gain potential energy. So this means the overall mass of nucleons separated from each other will be larger than the mass of one nucleus where they're all together. So this is another example of the mass defect, which we can work out with our equation delta E equals delta mc squared, where we'll make delta m our subject. Now conversely, when the nucleons collate to form a nucleus, they'll lose potential energy as they're more stable because they've got that attractive strong force exerted on each other. So this would mean that the combined mass of the nucleons will be larger than the mass of the nucleus that's formed. So therefore, when the nucleons combine to form the nucleus, mass is then lost and it's turned into energy, which follows Einstein's postulate as stated previously. So this means, like we said before, that the combined mass of the nucleons is larger than the mass of the nucleus, which is the mass defect, which is calculated by delta m is equal to delta E over c squared. So let's have a look at this in a particular example. So from the definition of one atomic mass unit, one carbon nucleus has a mass of 12U. So the mass of one carbon nucleus is 12U, but if we work out the mass of 6 protons and 6 neutrons, well then the mass of them individually is 12.096 U. So this tells us that the mass of a nucleus is always less than the total mass of the individual nucleons from which it's made. The difference between the mass of the nucleus and the total mass of the individual nucleons is called the mass defect of the nucleus, which we can calculate with the equation shown on the screen. Now we can calculate our mass defect in either kilograms or atomic mass units. Now in the process of nuclear fusion, nuclear fission and radioactive decay, each process produces a mass defect as the stability is increased. That's why we carry out those processes, to increase the stability of the nucleus. So this allows energy to be produced. So suppose all the nucleons in a nucleus were separated from each other. The extra energy needed for the nucleons to exist freely in the universe is the binding energy. So it's the energy required to overcome the strong force attraction in the nucleus. And the binding energy of each elementary nucleus is dependent on the size of the strong force there, which we can calculate by the equation delta E is equal to delta mc squared. So what we can say is the work that's done to separate a nucleus into all of its constituent nucleons is called the binding energy. Now the equivalent mass to this binding energy is known as the mass defect. Now we can calculate our mass defect or our binding energy with our equation. Binding energy is equal to mass defect times by c squared. But actually there's also a shortcut here, because if the mass defect is given in U atomic mass units, then the equivalent binding energy can be worked out by our following shortcut. Binding energy in MeV is equal to the mass defect in U times by 931.3. Now this method replaces the equation delta E equals delta mc squared. So we can also rearrange that and say we can work out our mass defect in U by doing our binding energy in MeV divided by 931.3. So to clarify, the binding energy of a nucleus is defined as the energy required to separate all of the nucleons in a nucleus. This is the energy needed to provide the extra mass required for all the nucleons to exist separately. It's the energy equivalent of the mass defect. So the binding energy in joules is equal to the mass defect in kilograms times by c squared. Now it can also be useful to calculate the binding energy in MeV from the mass defect in atomic mass units, where binding energy in MeV is equal to the mass defect in U U times by 931.3. Because remember, 1 U is equal to 931.3 MeV. So it'll make the equation a lot easier to carry out. So let's have a look at an example of calculating the mass defect. The mass of a nucleus of potassium of 40 K with a proton number of 19 is 39.9536 U, and the mass of a proton is 1.00728 U, and the mass of a neutron is 1.00867 U. Calculate the mass defect of the nucleus in U. Well, firstly, the first step is you've got to derive the number of protons and neutrons. So you work out your number of protons, your number of neutrons. You then determine the mass of the actual nucleons themselves. So you work out the mass of the protons and the mass of the neutrons in U. You then determine the mass defect of the nucleus by doing your mass defect. It's going to be equal, or mass deficit, sorry, is equal to the mass of the nucleons minus the mass of the nucleus. So it's 40.30239 U minus 39.9536 U is equal to 0.36679 U. Another example question might ask you to calculate the actual binding energy of the nucleus in MeV. So the mass of a nucleus of potassium 40, which has a proton number of 19, is 39.9536 U. The mass of a proton is 1.00728 U, and the mass of a neutron is 1.00867 U. Calculate the binding energy of the nucleus in MeV. So like I said before, you derive your number of protons and neutrons, you determine the mass of your nucleons, you determine the mass defect of the nucleus, and then you can then determine the binding energy of the nucleus by times in your mass defect by times by 931.3. So in this case, our mass defect is equal to 0.36679 times by 931.3 is 342 MeV. If you then wanted to, you can then convert this into joules by using the equation 1 MeV is equal to 1.6 times 10 to the minus 13 joules. Now this tends to be a faster method than using the equation delta E is equal to delta MC squared. So how can we learn in today's lesson? We can appreciate that E equals mc squared applies to all energy changes, carry out simple calculations involving mass difference and binding energy, have our atomic mass unit equal U, and have our conversion of units of 1 U is equal to 931.3 MeV. So if we've been successful and we've learnt in today's lesson, we can describe the nuclear processes of releasing energy, calculate the binding energy of the nuclear process, and define and describe the concept of binding energy. So I hope you've enjoyed today's lesson on binding energy, which is part of the nuclear physics topic in AQA A-level physics. Thank you very much for watching and have a lovely day. Hello and welcome to this lesson on binding energy per nucleon, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson, we're going to try and explain why some nuclei are unstable. So if we've been successful and learned in today's lesson, we should be able to calculate the binding energy of a nuclear process, define and describe the concept of binding energy, and then link binding energy per nucleon to nuclear stability, which links into the following part of the AQA A-level physics specification, 3.8.1.6 mass and energy. So in a previous lesson, we defined the concept of binding energy in nuclear physics. So the combined mass of free nucleons is slightly larger than the combined mass of bound nucleons in a nucleus. Now we call this mass difference the mass deficit or mass defect. Now this occurs as the nucleons are more stable in a nucleus, so they contain less potential energy due to the strong interaction attracting those particles together because they're close to each other. They're within the range of the strong interaction. Now this reduction in mass and therefore energy as the nucleons turn into a nucleus is called the mass defect. Now this mass defect can be converted into a potential energy value by using our equation delta E equals delta MC squared. We can also convert it into a potential energy value in MeV by using our equation delta E is equal to delta M times by 931.3, where our change in mass, our mass defect is measured in atomic mass units or U. Now this energy difference between the combined energy of the free nucleons and the bound nucleus can be emitted to the surroundings during the process of the formation of the nucleus. So this energy difference between the combined energy of the free nucleons and the energy of the bound nucleus is called our binding energy. So the binding energy is the work done to overcome the strong interaction attraction between all nucleons in a nucleus. So the binding energy is the energy needed to separate all of the nucleons in a nucleus into its separate nucleons. So we're now going to consider why this is so important. So the calculation of nuclear binding energy led to physicists pondering its importance to nuclear stability. So when we consider like two nuclei, so let's consider the nucleus of uranium, the largest naturally occurring nucleus in the universe, and helium, which is the smallest nucleus in the universe which contains neutrons. So we can say that the binding energy of a uranium nucleus is 1801 MeV, whilst the binding energy of a helium nucleus is only 28 MeV. Now it has been found that the larger nuclei, which have the greater number of nucleons, you would have the larger binding energy. So why do larger nuclei have a greater binding energy? Well, we find this is the case because the larger the nucleus, the greater the strong force attraction needed to overcome, so therefore the greater the binding energy. In addition, just a larger nucleus means there's a greater amount of nucleons, so you'll need a greater amount of total energy needed to remove all of them. So this in theory should mean it would take more energy to separate the larger nuclei than the smaller nuclei, as they've got a higher value of binding energy, because the uranium will need a lot more energy to separate all of its nucleons compared to the helium. So this means that the larger the nucleus, the greater the stability effect of turning free nucleons into a bound nucleus. So in theory it was pondered that this should therefore mean that the larger the nucleus of your element, the more stable the nucleus. However, it's found that larger nuclei tend to actually be more unstable because they tend to be alpha emitters, which goes against the theory of binding energy. So why do these larger nuclei tend to be unstable? Well, they tend to be unstable because the stability of a nucleus is not based on the binding energy, but rather the binding energy per nucleon, which is equal to the binding energy calculated divided by the number of nucleons in the nucleus. So it tells us how tightly bound each nucleon is to the nucleus on average. So the binding energy per nucleon is a much more accurate measurement of instability, because nuclear decays tend to only cause a few nucleons, a maximum of 4 in alpha decay, to be changed. So this means that the total energy to separate all nucleons is not actually an accurate measure of this particular process. So in a nuclear decay, the total nucleus is never separated. As a result, the binding energy does not have to be given to the nucleus to actually make them decay. We can consider this example by thinking about throwing a stone down a well, because if you throw a stone down a well, then the total amount of energy transferred depends on two things. Firstly, how deep the well is when you throw your stone down, and also how many stones you throw down in total. But whether actually an individual stone is likely to find its way out of the well again only depends on how deep the well is. It doesn't affect about how many other stones you've thrown down the well. This is the same idea with the nucleus, because the stability of a nucleus, i.e. whether it's going to fall to pieces or not, depends on the average binding energy per nucleus, which in this example is a measure of how deep the well is, rather than the total binding energy, which is a measure of how much energy is transferred by dropping everything in it. So unlike real wells though, the potential energy well of a nucleus changes its depth depending on how big the nucleus is. So as you make a nucleus bigger from scratch, it does get deeper quite rapidly, and then after about 56 nucleons it gets gradually shallower the more that you add. So the binding energy per nucleon is the average work done required to move one nucleon from the nucleus. So it's the amount of energy on average needed to be given to a nucleon as potential energy to overcome the strong force attraction. So the greater the average binding energy per nucleon of a nucleus, the more work needed to be done on average to remove just one nucleon from the nucleus, so therefore the more stable the nucleus is. So in a nuclear process, it is in fact the change in binding energy per nucleon which determines whether a process happens. So the greater the change in binding energy per nucleon, the greater the stability effect of the process, the more likely it is to happen. So let's just look at an example where we can see how to calculate the binding energy per nucleon. So what is the binding energy per nucleon nucleon of a 56 iron nucleus, which has a mass of 55.92067 U. So the first thing you've got to do in this particular type of question is find the mass defect, which is the mass difference by doing your mass of your individual protons and neutrons. Remember, you are given the proton and neutron mass in the back of the equation book, and then you would subtract that from the mass of the nucleus in total. So we've done 26 times by 1.00728, which is, if you look on here, going to be the number of protons, which you know that because you can work out how many protons are in iron, plus 30 times by 1.00867, which is the number of neutrons, which is 56, minus the number of protons, minus 55.92067, which is the mass of our nucleus in total. We can then find the binding energy, and again, remember that shortcut we talked about at the start of the video. You can multiply your mass difference in U by 931.3 to get into MeV, so we get 492.39 MeV. Then the third step is to divide this number by the number of nucleons. There's 56 protons and neutrons in iron. You divide that total by 56 and you get 8.7927 MeV. Now again, please remember, the higher the binding energy per nucleon, the more stable the nucleus is. Now, the change in binding energy per nucleon in a nuclear process determines if it occurs in nature. Now, we can demonstrate this effect when we graph binding energy per nucleon against mass number. So this graph will show us which elements are the most stable in the universe. Now, on this particular graph, the y-axis shows the binding energy per nucleon, how tightly bound our nucleus is, whilst the x-axis shows the mass number, the number of nucleons in the nucleus. Now, please remember, the higher the binding energy per nucleon, the more stable the nucleus is. Now, you'll notice straight away that iron is the most stable nucleus because it has the highest binding energy per nucleon. It's at the peak of the graph. So we can say that iron's the most stable nucleus because it requires the most energy to remove a nucleon from the nucleus. So we can actually determine what's our most stable nuclei in the universe by using this particular graph. Now, we can also remember that iron, by definition, is the most tightly bound nucleus. It's the most stable nucleus because it requires the most energy to remove a nucleon from the nucleus. Now, it's the aim of all elements to be as stable as possible, to basically increase their binding energy per nucleon to that of iron. Now, again, remember that when the average binding energy per nucleon increases, energy is released in this nuclear process, and the change in the binding energy gives you the total energy released in the nuclear process. So the average binding energy per nucleon can be used to estimate the energy released in different nuclear reactions. So for nuclei which are smaller than iron, when they fuse, okay, the binding energy per nucleon increases and they become more stable. So remember, again, the higher the binding energy per nucleon, the less energetic the nucleons are in the nucleus, the more stable the nucleus is. So energy will be given out in this process, and that's why energy is given out through nuclear fusion. Now, for nuclei larger than iron, when they fission, the binding energy per nucleon increases, so they become more stable. So again, remember, the higher the binding energy per nucleon, the less energetic the particles are in the nucleus, the more stable they are, so this energy can then be released in the nuclear fission process. So from looking at this graph, we can see straight away that there's two major areas of isotopes. Isotopes which carry out fusion, which is all the isotopes before iron, the peak of this graph, in our particular periodic table, whilst the isotopes which carry out fission, which are those ones which are above iron in the periodic table, as you'll see below the peak of iron in this graph. So isotopes lower than iron will fuse as this increases the binding energy per nucleon of an isotope, whilst isotopes higher than iron will fission, as again this increases the average binding energy per nucleon of the isotope. So you'll notice that the average binding energy per nucleon increases gently for heavier nuclei, those isotopes beyond iron, whilst the average binding energy per nucleon increases rapidly for those lighter nuclei carrying out nuclear fusion. So what this means is that the process of fusion increases the binding energy per nucleon of the isotope at a higher rate than fission does. So this means that nuclear fusion increases the nuclear stability much more easily than nuclear fission, which fundamentally means that the nuclear fusion process releases more energy per kilogram than the nuclear fission one. So what can we summarise from today's lesson? Firstly, we can carry out simple calculations from nuclear masses of energy released in the nuclear fission and nuclear fusion reactions. We can look at a graph of average binding energy per nucleon against nucleon number, and you should be expected to identify on the plot the regions where nuclei will release energy when undergoing fission and when they release energy when undergoing fusion. So if we've been successful and learnt in today's lesson, we should be able to calculate the binding energy of a nuclear process. We can define and describe the concept of binding energy, and finally we can link the binding energy per nucleon to nuclear stability. So thank you very much for watching this lesson on the binding energy per nucleon, which is a topic in the nuclear physics section of AQA A-level physics. Thank you very much for watching, and as always, have a lovely day. Hello and welcome to this lesson on nuclear fission, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson we're going to look at explaining the process of nuclear fission. So if we've been successful and we've learnt in today's lesson, we can describe what the process of nuclear fission is. We can construct a chain reaction diagram based on nuclear fission, then we can understand the different types of chain reaction in nuclear fission, which links into the following part of the AQA A-level physics specification. 3.8.1.6 mass and energy. Now in the previous lesson we've defined the concept of binding energy in nuclear physics. So the reduction in mass as nucleons turn into a nucleus is called the mass defect. Now this mass defect can be converted into a potential energy value by using our equation delta E equals delta mc squared, or you can work it out in the value of MeV by using our equation delta E equals delta M in U times by 931.3. Now, this energy difference between the combined energy of the free nucleons and the bound nucleus can be emitted to the surroundings during the process of formation. So this energy difference between the combined energy of the free nucleons and the bound nucleus is called the binding energy. So the binding energy is the work done to overcome the strong interaction attraction between all the nucleons in a nucleus. So the binding energy is the energy needed to separate all of the nucleons in a nucleus into its separate nucleons. However, in a nuclear process, the total binding energy does not indicate stability, as not all nucleons are separated. Only a few nucleons are removed in the decay process. So a better measure of stability in nuclei is the binding energy per nucleon, which is the work done needed to remove one nucleon on average from the nucleus, which is similar to a decay event. Now the higher the binding energy per nucleon of a nucleus, the higher the stability of the nucleus. So because iron has the highest binding energy per nucleon in the universe, this makes its nucleus the most stable configuration possible. Now all nuclear events such as fission, fusion or decay wish to increase the binding energy per nucleon of the nuclei. Now the greater the increase in binding energy per nucleon in the nuclei, the greater the increase in stability, so the greater the energy released by the process. Now fusion has a greater increase in binding energy per nucleon than fission, so each fusion event releases more energy than each fission event. But let's consider what fission actually is. Now uranium is a very important element in the universe. It's the largest naturally occurring element. So it's the element with the largest nuclear radius, and it's the element with the largest binding energy in the universe. Now physicists consider that if uranium is the largest nucleus in the universe, could we add to this nucleus to make even larger elements? Could we in fact transmutate uranium? Now in 1938, the physicists Hahn and Strassmann bombarded the uranium nucleus with neutrons. Now these neutrons were accepted by the nucleus, and the physicists were eager to analyse the new elements that were formed. So we thought that fame, fortune and new entry in the periodic table awaited. Now just to clarify, a neutron was used as it only has the strong attractive force and not the repulsive electrostatic force, allowing it to lower the binding energy per nucleon even further. However, they discovered that actually there wasn't any larger elements present, but there were actually many lighter elements such as barium present after the bombardment, even though that the uranium was pure before and there was no heavier elements. So there could only be one conclusion, that the uranium nuclei was split into approximately 2 equal fragments of nuclei. Now this process increased the binding energy per nucleon of the daughter nuclei. So this process increased the nuclear stability of our daughter nuclei. So what what the two physicists had discovered was the concept of nuclear fission, which we're going to cover in today's lesson. Now, in nuclei larger than iron, they have a smaller binding energy per nucleon than iron. This means that the nuclei are not as tightly bound, so the nucleus does not exist in a lower energy state. So this makes our nuclei unstable, and so the nucleus could carry out radioactive decay such as alpha decay. However, the radioactive decay would still leave the nucleus with a lower binding energy per nucleon than iron, so the nucleus could still become more stable. So the nucleus could carry out an extreme form of decay. It could split into two fragments. It could carry out nuclear fission. So what nuclear fission is our large nucleus with a large nuclear radius split into two smaller nuclei which are more stable because they've got a smaller nuclear radius and they've got a higher binding energy per nucleon. Now, the aim of the nuclear fission is to increase the binding energy per nucleon of the nucleus, and the difference in binding energy is given out in the nuclear fission process. So energy is released. Now, in the fission process, some of the mass is lost in the fission process. So the total mass before is greater than the total mass after. So this mass is converted into energy by our equation delta E equals delta mc squared and given out in the fission process. Now, the energy tends to be released in either the form of kinetic energy the particles released or in the form of gamma photons. Now, the nuclei produced in fission exist in a lower energy state than the nucleus at the start. So this excess energy is shed by the nucleus and given out in the process. Because again, remember, the aim of nuclear fission is to increase the binding energy per nucleon. So to understand how fission works, we've got to consider the complete process. So consider one unstable uranium nucleus. Well, a neutron is then fired to this uranium nucleus. Now, the neutron is accepted into the nucleus because the neutron will be accepted because it provides an extra strong force with no electrostatic repulsion. Now, this neutron will induce fission, so we call it induced fission. Now, only low energy neutrons can be captured this way. Now, we call a low energy neutron a thermal neutron because the neutron is in thermal equilibrium with its surroundings. Now, on rare instances, nuclei can fission naturally, which we call spontaneous fission. Now, the larger the nucleus, the more unstable it will be, so large nuclei are more likely to spontaneously fission. Now, spontaneously fissioning limits the number of nucleons that a nucleus can contain, so it limits the number of possible elements. So like we mentioned before, for a neutron to be accepted in induced fission, the nucleus must be travelling at a particular speed. Too fast and will smash straight through the nucleus. Too slow and will not be able to get close enough to the nucleus. Now, the addition of the neutron to the nucleus makes the nucleus extremely unstable. Now, the added neutron lowers the binding energy per nucleon. The increase in strong force is not offset by the extra mass, so it makes the nucleus more unstable. So we've now got an even lower binding energy per nucleon and an even more unstable nucleus. The uranium nucleus then splits into two smaller nuclei. Now, the two smaller nuclei have a higher binding energy per nucleon, which makes our nuclei more stable. So we've increased our binding energy per nucleon for each of our two products. Now, heavy nuclei do not always fission to form the same daughter nuclei. The uranium can split into lots of different pairs of nuclei with nucleon numbers of around 90 to 140. Now, it's important that we've increased the stability of our nuclei in this particular process. Now, this process will also produce lots of energy. Per kilogram, there's about 1,000 times more energy this way than by combusting coal. So now, nuclear fission process, energy is released. So the excess energy shed by the nucleus is given off as energy. Mass is turned into energy, and this is equivalent to the mass lost in the process. So energy is released to the surroundings due to the mass deficit principle. Now, it's important to note that this energy released in fission, is what is used to heat water in power stations for nuclear power stations. Now, this energy released in fission is found initially in the form of kinetic energy, the products in the event, or gamma photons. Now, we can work out the energy released in this particular nuclear fission event by doing delta E equals delta mc squared, or we can say the energy released in MeV is the mass defect in U times by 931.3. So let's look at a particular example. So very large atoms are unstable because their nuclei are too large to be held together by the short-range strong nuclear forces effectively. Taking away the nucleons therefore increases their stability, binds them more tightly, and releases energy. So find the energy released when the uranium-235 nucleus undergoes nuclear fission according to that following equation. So the first step is to calculate the masses in U before and after. Then the second step is then to calculate the mass defect. So what you would do is in your mass defect, you would work out the mass of the nucleons afterwards. Okay, you work out the mass of the products before, so of the reactants before. So therefore you find the difference and we get our value in U. We can then calculate our binding energy by timesing our mass difference in U by 931.3 and we get that in MeV. So in this example we found that each uranium nucleus releases 173 MeV of energy when it fissions. Now it's important to note that there's lots of energy released per kilogram in nuclear fission, because whilst one fission event produces little energy via the mass defect, there's so many uranium nuclei fissioning in one sample of radioactive uranium, the total energy released is very large. Now the fission process also produces 3 neutrons in this when it splits as well. Now as the fission process are linked in a chain, because these neutrons will go on and then fission other uranium nuclei, we call this a chain reaction. Now only uranium-235 nuclei will fission, uranium-238 nuclei do not fission. So it tells us that the greater the amount of uranium-235, the greater the amount of uranium fission that will be carried out. Now we can artificially increase the amount of uranium-235 in a uranium substance, and we call this enriching uranium. Now why does uranium-238 not fission? Well, if a neutron encounters uranium-235, it will be absorbed and become uranium-239. Uranium-239 can then beta decay into neptunium-238, and then neptunium-238 can beta decay into plutonium-239, but you don't get this fission process. So, the capture of a neutron by a nucleus of uranium-238 leads to the formation within a few days of a nucleus of plutonium-239, which actually is also fissile. Now, the nucleus of uranium-239 resulting from the capture of a neutron is a radioactive beta minus emission after that. So, by emitting your electron and antineutrino, it can become neptunium, which then becomes itself unstable and transforms in the same way to plutonium-239. Now, plutonium can also fission, and this allows extra fission to occur in your fission generator. Now the amount of plutonium produced needs to be monitored in a nuclear reactor in case it can cause the chain reaction to increase. Now we've got to consider what's going to happen to the fission rate in this chain reaction. So let's assume each fission when an event releases 3 neutrons when it takes place. So when you start off with 1 neutron being fired at the nucleus, you'll then get 3 being formed. Now each of those 3 neutrons will then find a nucleus, and each of those nuclei is going to produce 3 neutrons in the fission process. So it goes to 9, then it'll go to 27, then it'll go to 81, so on, so on, so on. Now this is what we call an uncontrolled chain reaction. There's been no measures taken place to change the fission rate. So what will happen is, in this case, we call this a supercritical chain reaction, because each time in each step of the process the energy released by the mass defect is increasing, so eventually it'll produce so much energy that the reactor will explode, which we call a nuclear reaction. So it's an uncontrolled chain reaction. At each step of the fission chain, the fission events are releasing a greater cumulative amount of energy. Now, it's important to note that when the energy is released is large enough to actually melt the uranium fuel rod, we say our chain reaction is in meltdown. So nuclear weapons can contain an uncontrolled chain reaction. So we've got to be very careful about how we carry out these processes. So we say, like I said before, our chain reaction is supercritical. So this occurs when the fission rate increases exponentially, and this will happen naturally after a process has been induced and nothing's been monitored. Now, we've got to control our chain reaction by trying to ensure the number of neutrons fissioning uranium stays consistent. So again, if we consider that each fission event releases 3 neutrons, we can stop 2 out of 3 causing further fissioning by encountering other uranium nuclei. So we can go from 1 to 1 to 1 to 1 to 1. Now if this happens in a nuclear power station, we say that the power station is producing power at a steady rate, so the process has gone critical. So the mass of uranium needed to do this is called the critical mass, which is very good. So we say at this point our chain reaction is critical, and this occurs when the fission rate stays constant. This actually happens when control rods are placed partially into the reaction chamber. Now if measures are needed to stop the chain reaction process, all of our fissile neutrons must be stopped from encountering the uranium, so it'll go from 1 to 1 and then eventually stop. So if this happens in a nuclear power station, the fission process stops and no more energy is released by the fission process. So our process has gone subcritical. All the engineering in a power station is to ensure this takes place when a nuclear power plant goes into emergency shutdown. So we've got our chain reaction being subcritical. So this occurs when our fission rate decreases, and this will happen when the control rods are placed fully into the reaction chamber. So let's have a summary of our different types of chain reactions for the fission process. So if you've got a subcritical fission chain reaction, the fission rate will decrease to 0. Now this is achieved by fully placing control rods into the reactor vessel, and the chain reaction ceases and no more energy is released. You have a critical chain reaction where the fission rate remains constant. Here you can place control rods partially into the reactor vessel and you get a constant supply of energy released, while supercritical is when the fission rate increases exponentially. This is allowing the induced fission process to occur naturally and put no measures in place to halt it. You will then get enough energy released eventually to cause a nuclear meltdown. So in our lesson we should have hopefully looked at both the fission process and we'll look at the fusion process next time, and we'll have simple calculations from nuclear masses of energy released in the fission reaction. So if we've been successful and we've learnt in today's lesson, we should be able to describe what the process of nuclear fission is, construct a chain reaction diagram based on nuclear fission, and then finally understand the different types of chain reaction in nuclear fission. So I hope you've enjoyed today's lesson on nuclear fission, which is part of the nuclear physics topic in AQA A-level physics. Thank you very much for watching and have a lovely day. Hello and welcome to this lesson on induced fission, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson we're going to look at explaining at how a power station carries out fission safely. So if we've been successful and we've learnt in today's lesson, we should be able to explain how a nuclear fission reactor works, describe a thermal nuclear fission reactor, and explain how a nuclear fission chain reaction is controlled, which links into the following part of the AQA A-level physics specification, 3.8.1.7, induced fission. So a nuclear reactor uses a controlled chain reaction to produce heat, to produce steam for a generator. Now apart from the source of heat, it works in the same way as a coal-fired power station. So if we look at the actual reactor vessel itself in the fission power station, you can see that the nuclear fission process takes place in this steel vessel. Now we've got to consider the processes which take place inside this steel vessel, because if we wish to understand the fission process in a fission generator, we can then understand the processes inside a nuclear power station. So as mentioned before, nuclear fission is a chain reaction. Now for a chain reaction to occur at all, a critical mass of fissile material is needed. Now critical mass is the minimum amount of mass needed for a sustained chain reaction to occur in a material. So if we consider that as our definition for critical mass, why does a critical mass exist at all in the fission process? Well, it's because the chain reaction takes place because neutrons released in the original fission event will then go on to encounter other nuclei and then cause them to fission as well. But some of the fission neutrons will escape out of the fuel rods without causing fission because they'll just not encounter another nucleus of uranium. So it's dependent on the surface area to mass ratio of the material, because if it's too high, there's a greater chance of the neutron escaping from the reactor without encountering a nucleus which it can then fission. So the mass has to be increased to a certain amount to ensure that these neutrons, when they're produced in the fission process, will collide with another unstable nuclei. So the critical mass is dependent on the surface area of our fuel rod. So the critical mass occurs as not all the neutrons will hit a fissile uranium nucleus before escaping the rod. Now we've mentioned the fact that it's got to hit a fissile uranium nucleus. Well, why is that? Well, it's because the fuel rods in the reactor core contain different types of uranium, different isotopes of uranium. Now naturally only uranium-235 will fission when it absorbs a neutron. Now natural uranium contains 1% uranium-235. So the greater the amount of uranium-235, the more fission that will occur, so there's a greater chance of a chain reaction developing in our reactor vessel. So physicists have developed enriched uranium to ensure a chain reaction is produced in a reactor. Now, enriched uranium contains about 3% uranium-235 as opposed to 1% uranium-235, which is still a very small amount, but it does take a long time to carry out the enrichment process. Interestingly, a fission bomb contains about 50% uranium-235. Now, many countries wish to develop the ability to produce enriched uranium. However, developed countries do not like to share how this is produced because the enriched uranium tends to be produced in secure locations in that country. Now, we note that when we're doing the fission process, we need to enrich uranium fuel until it reaches its critical mass, because once it's reached its critical mass, a sustained chain reaction can take place. Now, as mentioned before, how do we ensure the chain reaction stays critical and doesn't go supercritical in its fission process? So there are three main features of a nuclear reactor in a power station which helps maintain a steady fission rate with a critical chain reaction in the reactor vessel. You've got the control rods, the coolant and the moderator. So we're now going to investigate how each component works. Now, control rods in the reactor vessel absorb extra neutrons which keeps the chain reaction under control. The depths of the rods in the core can be changed to maintain a steady reaction rate. Now, our control rods are generally made out of boron because they absorb excess neutrons and they actually become radioactive waste after the process. So control rods are needed to prevent a reactor core from going into nuclear meltdown. So control rods are required in nuclear power stations to prevent large-scale nuclear accidents. So in a reactor vessel there are two types of rod. You've got your fuel rods, and these rods contain enriched uranium, which is found in the form of uranium oxide. Now, these rods are where the fission process takes place. You've also got control rods, which are rods made from boron. These rods are where the fissile neutrons are absorbed. Now, for every fission reaction, on average 3 neutrons are produced. So for a controlled chain reaction, only 1 neutron can be allowed to fission. So this means the control rod on average absorbs 2 out of every 3 neutrons. So for the reactor to transfer energy at a constant rate, each nuclear fission reaction must lead to 1 more fission reaction. Since each reaction gives out 2 or more neutrons, we've got to remove some of these extra neutrons. So like we said before, the control rod absorbs neutrons, reduce the amount of nuclear fission processes occurring and making the power output of our nuclear power station constant. So it's important to note that the depth of the control rods in the core is automatically adjusted to keep the number of neutrons in the core constant, so exactly 1 fission neutron per fission event on average goes on to produce further fission. So this condition keeps the rate of fission energy release constant. So it's important to note that we can lower our control rods further into the fuel rods to absorb more neutrons and further reduce the amount of fissioning. Now, also as well, some neutrons leave the reactor interfering and some travel too fast, while others are absorbed by uranium-238. So it's not an exact science that the control rod itself needs to absorb 2 out of every 3. Now, if we need more neutrons, okay, we can raise our control rods further. So if the fission rate's dropping, we can actually pull our control rods out of the reactor vessel. Now, the emergency shutdown procedure of a nuclear power station is actually to fully insert the control rods into the reactor vessel. This will ensure all neutrons are absorbed and no further fission can take place. This will cause our chain reaction to go subcritical. It's also important to note that this process of the control rod absorbing neutrons will make the control rod radioactive after use. So this makes the control rod nuclear waste which needs to be buried. So what is our factors that affect the choice of material used for your control rod? It's the ability to absorb neutrons and having a high melting point, because it gets very hot in the reactor vessel and you don't want it to melt. So the typical materials used are either boron or cadmium. Now, the absorption of neutrons increases the number of neutrons in the boron nuclei and makes them unstable, which makes them nuclear waste. The second thing we've got to look at is the coolant. Now, water acts as a coolant in a reactor vessel. So the water molecules gain kinetic energy from the neutrons and the fuel rods, and the water is pumped throughout the core and through seal pipes to and from a heat exchanger outside the core. So the role of the coolant is to carry heat, okay, and exchange it into our actual power station. So the pressurizer and pump move the hot coolant to the heat exchanger, and the hot coolant touches the pipes carrying cold water, water. So the heat flows from the hot coolant to the cold water, turning our water into steam and leaving the coolant. The steam will then leave the reactor and turn the turbine as the coolant returns to the reactor. So fission fragments in the fission process transfer kinetic energy to coolant molecules via collisions. So the energy released via nuclear fission transfers via kinetic energy of the fission fragments. The fission fragments released via nuclear fission will then collide with the coolant molecules, and this transfers energy from our fission fragment to our coolant molecules. Now the collisions are inelastic, however they do cause our coolant molecules to heat up. So firstly, this prevents the reactor core from overheating and causing a uranium meltdown. Now in older power stations we tended to use our carbon dioxide molecules as the coolant, but in newer power stations the coolant molecules are water molecules. Now the coolant needs to be very efficient at transferring heat, because not only does it stop our uranium from going into nuclear meltdown, but the heat from the reactor can also be used to make steam for powering electricity generated turbines. So what factors affect the choice of material for our coolant? Well, it must be able to carry large amounts of heat, be either a gas or a liquid, be non-corrosive, non-flammable and a poor neutron absorber, so it's not going to become radioactive. So typical materials can either be carbon dioxide or water. Now the final thing we need to consider is the moderator. Now fission neutrons are slowed down by collisions with atoms in the water molecule, atoms of the water molecules. Now this is needed as fast neutrons do not cause further fission of uranium. So too fast and the neutrons smash straight through the nucleus, and too slow, the neutrons will not be accepted by the nucleus. So the water is a moderator because it slows down the fast neutrons to just the right velocity. So if the neutron is going too fast or too slow, it will go through the uranium. It just needs to be going at just the right velocity. So fission neutrons need to be slowed down significantly to cause further fission of uranium-235 nuclei, otherwise they'd be travelling too fast to be accepted by the nucleus. They would literally just collide off the nucleus. So a neutron, which is travelling at a speed to be absorbed by a uranium nucleus, is called a thermal neutron. Now why is this? It's because the neutron is a thermal equilibrium with its surroundings. Now choosing a moderator with a similar mass to the neutrons allows that moderator to be more efficient at slowing down the neutrons. Now as we mentioned before, if the neutron has too much energy, it will pass straight through the nucleus. If the neutron has too little energy, it will pass away from the nucleus. So the neutron needs to be slowed to just the right speed to be accepted by the nucleus. Now the moderator slows down the neutron by colliding with it. So the neutrons are slowed down by collisions with other molecules in the reactor. Now this is normally water, as found in older reactors, or liquid graphite in our new reactors. If the reactor core had a vacuum surrounding the fuel rods, this chain reaction just would not work because the neutrons would be travelling too quickly. Now each collision between the neutron and the moderator molecule is an elastic collision. So this means the kinetic energy and the momentum of the fissile neutron is transferred to the moderator molecules. So the transfer of the momentum and kinetic energy to the moderator molecules heats up the moderator. So it's very similar in action to that of the coolant. So this is how in many examples the moderator and the coolant in our nuclear fission reactor are in fact the same substance. So like mentioned before, in older power stations the moderator molecules are graphite, whilst in newer power stations the moderator molecules are water molecules. Now assuming that the collision of a moderator particle and a neutron is perfectly elastic, you know that the kinetic energy and the momentum are both conserved. Now if we assume the moderator particle is stationary before the collision, we can write out the following equation. So we've got our mass of our neutron, our mass of our moderator, our mass and the masses stay constant before and after the collisions, and we've got our velocity of our neutron and our velocity of our moderator before and after the collision. Note before the collision the moderator is stationary, so the velocity will be 0. So if momentum is conserved, we can say that the momentum of the neutron, because the moderator has no momentum before the collision because it's not moving, is equal to the momentum of the neutron plus the momentum of the moderator. And it's the same idea for the kinetic energy, that the kinetic energy of the neutron before, because remember the moderator before has no kinetic energy because it's not moving, will equal the kinetic energy of the neutron plus the kinetic energy of the moderator after the collision. Now with these two equations, we can use these equations to find terms for the velocity of the neutron after the collision and the velocity of the moderator after the collision. So if we sub in our terms, we can see that this on the screen is the following equation for the neutron after the collision in terms of its velocity before the collision. And by that same logic, we can also find the velocity of the moderator after the collision in terms of velocities of the neutron before it. Now what's interesting to note is if we look at these two equations and we say that the mass of the moderator particle is equal to the mass of a neutron, well actually our final velocity of the neutron will be 0 meters per second, because we can say that it's going to be the velocity of the neutron after the collision is m minus m over m plus m times by the velocity before, which when we work it all through, m minus m equals 0, so we'll cancel it all through, so our final velocity of our neutron would equal 0. And also if we look at the velocity of the moderator, it'll actually have the velocity of the neutron before the collision, because we can say that it's going to be 2m over m plus m, which is just 2m again. They cancel through, times that by vn equals vn. So this indicates to us that all of the kinetic energy and the momentum will be transferred to the moderator particle. So the more similar the masses of the neutron and the moderator, the more kinetic energy and momentum will be transferred from the neutron to the moderator. So the moderator should be slowing the neutrons to about 2,200 meters per second to be absorbed by our uranium nuclei, so the mass of the moderator needs to be around the same size as the mass of the neutron. Now this entire reactor is placed inside a steel vessel. Why do we do this? Well, the steel vessel can withstand high temperatures and the pressures needed and produced by the fission events. Also, the steel vessel can absorb beta radiation and reduce gamma radiation / free neutrons produced in the fission events. But we also surround our steel vessel with thick concrete walls. Why is that? Well, the thick concrete walls will reduce the gamma radiation and the free neutrons even more so than the steel vessel would. So what can we summarize from today's lesson? Fission induced by thermal neutrons, we consider the possibility of a chain reaction in critical mass. We should know the functions of the moderator, the control rod and the coolant in a thermal nuclear reactor, and we can detail what's going on with all these particular ideas. We should have an understanding of a simple mechanical model of moderation by elastic collisions and factors affecting the choice of materials for the moderator, the control rod and the coolant, with examples of materials used for these particular functions. So, if we've been successful and we've learnt in today's lesson, we can explain how a nuclear fission reactor works. We can describe a thermal nuclear fission reactor and then explain how a nuclear fission chain reaction is controlled. So I hope you've enjoyed today's lesson on induced fission, which is part of the nuclear physics topic in AQA A-level physics. Thank you very much for watching and have a lovely day. Hello and welcome to this lesson on nuclear fusion, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson we're going to look at understanding the process of nuclear fusion. So if we've been successful and we've learned in today's lesson, we should be able to describe what nuclear fusion is, calculate how much energy is released in a nuclear fusion event, and understand the conditions needed for nuclear fusion to occur, which is part of the following part of the AQA A-level physics specification 3.8.1.6 mass in energy. So a very small mass defect in a nuclear process can lead to a lot of energy being produced in nuclear fission. This is because mass can be considered an extreme form of potential energy via our equation delta E equals delta mc squared. Now the mass defect principle indicates that a small defect in mass leads to a large amount of energy released in the process. However, nuclear decay and nuclear fission are not processes which release the most energy per kilogram in the universe. The process which releases the most energy per kilogram of radioactive material in the universe is nuclear fusion. Nuclear fusion is the process of two lighter nuclei combining to form a larger, more tightly packed nucleus. This leads to the biggest mass defect possible in the universe and as such the greatest energy released. So this leads to the greatest stability increase in nuclei in the universe and as such leads to the greatest energy released. So this is the process which is currently taking place in the core of all stars in our universe. Now the change in binding energy per nucleon in a nuclear process determines if it occurs. So we can demonstrate this effect when we graph the binding energy per nucleon against the mass number. So this graph shows the elements that are most stable in the universe. The higher the binding energy per nucleon, the more stable the nucleus is. Now iron is the most stable nucleus because it requires the most energy to remove a nucleon from the nucleus. It has the highest binding energy per nucleon in the universe. So it is in fact the most stable nucleus, the most tightly bound nucleus. So it's the aim of all elements to be as stable as possible to increase their binding energy per nucleon. Because remember that when the average binding energy per nucleon increases, the energy is released in the nuclear process. So for nuclei smaller than iron, when they fuse, the binding energy per nucleon increases, they become more stable. So we get an energy yield from this process, which we call fusion. Now for nuclei larger than iron, when they fission, the binding energy per nucleon increases, they become more stable. So that's the fission process. So you got the isotopes below iron, which carry out nuclear fusion, and the isotopes above iron, which carry out nuclear fission. Now isotopes lower than iron will fuse because this increases the average binding energy per nucleon of the isotope, and it's the same idea for isotopes higher than iron, that they will fission. So it's important to note though that for fission the average binding energy per nucleon increases gently for the heavier nuclei, but the average binding energy per nucleon below iron increases rapidly. So this means that the process of fusion increases the binding energy per nucleon of the isotope at a higher rate than fission does. So this means that nuclear fusion increases nuclear stability more easily than nuclear fission. It means that in nuclear fusion it will release more energy per kilogram than nuclear fission in a single event. So in the previous lesson we've considered nuclear fission. In today's lesson we're going to examine nuclear fusion. So what is nuclear fission? Nuclear fission occurs in elements above iron. It's when one large nucleus splits, and it tends to be an induced process by firing a neutron at that nucleus. Whilst nuclear fusion occurs in elements below iron, it's when two smaller nuclei combine, and it tends to be a spontaneous process. But both events will increase the binding energy per nucleon of the nuclei, and both events release energy via the mass defect principle. So fusion takes place when two nuclei combine to form a bigger, more stable nucleus. So beforehand you've got two lighter nuclei with a smaller binding energy per nucleon, and afterwards you've got a heavier nucleus with a larger binding energy per nucleon, so the nucleus is more tightly bound to the larger strong force, so it is more stable. So it's important to note that there's a larger strong force to overcome the electrostatic repulsion, so therefore the nucleons need less potential energy to exist in a stable formation, so this energy is then released in our from the nucleus in this process. So we can say that in this process the mass before and the mass afterwards are not equal. The total mass of the two smaller nuclei before is greater than the total mass of the one nucleus afterwards. So this mass change is converted into energy by our equation delta E equals delta mc squared, and is given out in the fusion process. But this process cannot occur with normal conditions found on Earth, because this fusion process can only take place if the two nuclei are being combined at high speed. That's because you've got two positively charged nuclei in the process before. So we need to overcome the electrostatic repulsion of the two positive nuclei so we can say that they combine. Now, so we say we need energy to overcome our Coulomb barrier of repulsion. Now it's also important to know that with our heavier nucleus, most of the kinetic energy is released as part of the mass defect. Now some of the kinetic energy remains as the kinetic energy of the larger nucleus, and the proportion depends on the size of the nucleus and the repulsion force of the original nuclei. So how do we overcome it? Well, we overcome it by having our two nuclei combine at high speed. Now we interpret this high speed of the nuclei as a high temperature. So about 1 MeV of kinetic energy is needed to make the nuclei fuse together. Nuclei with less kinetic energy will be deflected by the electrostatic repulsion. So for this to occur, the kinetic energy of the nuclei must not be fully converted into the potential energy of repulsion before they are within about 3 × 10⁻⁻15 meters of each other. Why is it going to be that particular range? Well, at that particular range the attractive strong force can take hold, and it can attract the two nuclei together and bind them to form one nucleus. So the nuclei just need to get within the range of the strong interaction. This then takes over and pulls the nuclei together. Now the chance of this occurring can be increased by carrying out our process under high pressure, because this high pressure will make the nuclei come come even closer together regardless of the kinetic energy each possesses, so it's more likely for it to be within the strong force interaction range, so they can bind the two nuclei together. So the conditions needed for fusion are as follows: high temperature and high pressure. Now, increasing the pressure will also increase the collision rate of the process as well, so therefore you're going to get a more likelihood of fusion taking place. Now, we should also be able to calculate the energy released during fusion by carrying out the following steps. The first step is to find the mass of the products and reactants in atomic mass units. The second step is then to find the mass defect in the process by subtracting the product mass from the reactant mass, and then finally step 3 is then using an equation convert the mass defect into the energy released. So if we put some numbers in, we can see that we can find the masses of the products and reactants in U, find the mass defect by subtracting the product mass from the reactant mass, then you can work out the energy in MeV by times by 931.3 to get into MeV. You could then convert it into joules later if you want. Now, examples of fusion in the universe include two protons coming together to form deuterium, a beta plus particle, a positron, and an electron neutrino. Now, the energy via mass defect released here during this fusion event is 0.4 MeV. Another example would be deuterium, which is an isotope of hydrogen, and a proton fusing together to form helium-3. Now, the energy released in this mass defect in this event is 5.5 MeV. And finally, you could have two helium-3 nuclei coming together to form helium-4 and two protons. Now, the energy released by the mass defect principle here is 12.9 MeV per fusion event. Now, actually, our sun carries out all three of these processes in its core, and we call this the proton-proton chain. It's the fusion chain process that occurs in all smaller stars when they turn hydrogen into helium. Now, this is actually the reason why the sun gives off a tremendous amount of neutrinos every second, because neutrinos are produced in the first fission event of when we're turning our two hydrogen nuclei into our deuterium isotope. Now, it's also the reason why the sun is constantly giving off energy in the form of radiation and losing its mass, because the sun is losing its mass via the mass defect principle to produce electromagnetic radiation. Now, rather interestingly, all three processes happen very quickly after each other within a matter of seconds in the core of the sun, but it takes about 100,000 years to travel from the core to the surface of the star itself. Now, as the sun carries out the three different fusion processes to produce a stable helium isotope, one chain process will release about 25 MeV. So this equates to about 6 MeV per nucleon, which is a lot more than the energy released per nucleon in a fission event, which is actually why most nuclei below iron wish to carry out nuclear fusion. It's why fusion provides the most energy per kilogram in the universe. So throughout most of the sun's life cycle, energy is being produced by the nuclear fusion in the core region through the steps we looked at before, the proton-proton chain. Only about 0.8% of the sun's energy generation comes from what we call the CNO cycle, which is the fusion of heavier elements such as carbon, nitrogen and oxygen, but this proportion is going to increase as the sun becomes older. Now, the core is the only region in the sun that produces an appreciable amount of thermal energy through fusion, because you need the high temperature and high pressure which is found in the core of the star. So 99% of the sun's power is generated in about 24% of the sun's radius, and by about 30% of the sun's radius, fusion has stopped nearly entirely because the temperature and pressure just isn't high enough for our nuclei to combine together. Now, fusing our 4 free protons, our hydrogen nuclei, into a helium nucleus releases about only 0.7% of that mass as energy. But we actually do know that in the proton-proton chain we get about 9.2 times 10 to the 37 events each second in the core, so we're converting about 3.7 times 10 to the 38 protons into helium nuclei every second, which then has a mass defect of about 6.2 times 10 to the 11 kilograms. So at this process we're actually converting about 4.26 million metric tons of hydrogen into energy, which gives us about a power rating of about 3.8 times 10 to the 26 watts. So in this lesson we've looked at the fusion process, and we can carry out simple calculations from nuclear masses of energy released in the fusion reaction. So if we've been successful and we've learned in today's lesson, we should be able to describe what nuclear fusion is, calculate how energy is released in a nuclear fusion event, and finally understand the conditions needed for nuclear fusion. So I hope you've enjoyed today's lesson, which has been on nuclear fusion, which is part of the AQA A-level physics topic of nuclear physics. Thank you very much for watching and have a lovely day. Hello and welcome to this lesson on radioactive waste, which is part of the nuclear physics topic in AQA A-level physics. So what we're going to do in today's lesson is we're going to detail the different types of radioactive waste and how they are treated. So if we've been successful and learnt in today's lesson, we should be able to explain how fuel rods can be disposed of, describe how radioactive material is removed from a plant, and then finally explain the balance of risks and benefits in the development of nuclear power. So we're going to be covering the following part of the AQA A-level physics specification, 3.8.1.8 safety aspects. So in an induced nuclear fission process, the following change takes place. Beforehand, you've got a uranium fuel and a startup neutron source, so either normally beryllium or polonium. Then after the fission process, you'll have some unused uranium fuel, smaller nuclei fragments from the fission process itself, used control rods and free neutrons. And in addition to this, you'll have energy released as kinetic energy of the products due to the mass defect. Now, the material afterwards is commonly called nuclear or radioactive waste, and it must be dealt with to ensure that it doesn't pose a health risk to the humans or the environment around it. So if we think of the following, before the fission process, you've got uranium-235 and uranium-238 isotopes. Now both these isotopes only emit alpha radiation naturally. Now this won't actually escape the fuel rod casing. So the reactants in this particular process are not going to pose a health risk to people in the surrounding environment. But after fission, the fragments of the nuclei produced in the fission process will emit beta or gamma radiation, because you tend to find that the products of nuclear fission tend to be very neutron rich in their composition, so are very radioactive. And in addition, in the fission process, you'll have times when uranium-238 encounters a neutron and turns into plutonium-239, which is actually a very active alpha emitter, which if not handled carefully can actually cause lung cancer. So the products of fission leave us a problem of what to do, not the actual reactants of the fission process. Now, the products of fission can be used practically in a medical diagnosis. However, fission is carried out at high temperatures and the fragments produce beta and gamma, so as such precautions need to be taken. Now, all radioactive waste presents a danger to humans. This is because radiation is a stochastic effect. This means there's no maximum safe dose. Any dose of radiation, no matter how small, can present a danger to human health. Now the higher the dose of radiation, so the higher the activity, the greater the risk to human health. So this leads us to classifying radioactive waste into three categories, each category with a different level of precaution in different storage method. So you've got high level radioactive waste, intermediate level radioactive waste and low level radioactive waste. Now most high level radioactive waste, which is the waste we think about when we consider radioactive waste, comes from nuclear power stations, hospitals using radioisotopes or specialist universities. Now it's important to note that in the UK the government policy states that the disposal of any form of radioactive waste must be in accordance with legal regulations and by approved disposal containers until its activity is insignificant, the same as the background. So all companies, all universities, all schools, all hospitals, all nuclear power stations must comply with this. But how do we dispose of each type of radioactive waste? Well, with low-level radioactive waste, which is objects such as lab equipment, protective clothing, or tools which have been contaminated in use, they're sealed in metal drums and buried in large trenches. Intermediate-level waste are objects with a low radiation activity or containers which held radioactive materials for a long period of time. Now, this waste is sealed in drums that are encased in concrete and then stored in specially constructed buildings. Now, these purpose-built buildings have walls of reinforced concrete. Now, again, here's a picture showing the outer structure of one of these buildings. Now, high-level radioactive waste tends to include the spent fuel rods, the fissile materials and the fuel cans, what we contain our fuel rods in. Now, this tends to include uranium-235, uranium-238 and plutonium-239. Now, it's important to note that what happens is the spent fuel rods are first removed by remote control, so a human doesn't actually handle them at any point, and they're stored in underwater or cooling ponds for approximately a year. This is because the fuel rods are still emitting thermal energy due to further radioactive decay, and the fuel rods are still emitting alpha radiation. So these underwater ponds firstly cool the fuel rods down, and secondly block any alpha radiation emitted by the fuel rod. Now, the fuel rods are then transferred to a large steel cask, and the unused uranium and the plutonium are removed for further use. Now, in the UK, this occurs in the Thorpe reprocessing plant found at the Sellafield power station. Now, it's important to note that the name of taking the unused uranium and recycling for another fission process is called reprocessing. So you can see here our reprocessing plant. After reprocessing, the unwanted materials are then stored in sealed containers in deep trenches, and this must be stored for centuries because they contain radioisotopes with long half-lives, so they can't contaminate the food chain or the water supply. So in the UK, containers of high-level radioactive waste are securely monitored at the Sellafield nuclear complex. So these containers of waste can only be accessed by workers at Sellafield. Now, other countries store radioactive waste in the same way or in underground caverns which are geologically stable. Now, some countries, such as the United States, mix the waste with molten glass to store them as glass blocks. Now, in the UK, we're now starting to turn our radioactive waste into molten glass. Now, the process of turning a substance into glass is called vitrification. Now, it's safer to keep our radioactive waste vitrified or as molten glass, since the radioactive waste cannot leak out of the container or become part of the water cycle in the environment. So here's a flow diagram showing how high-level waste is treated in the UK. In stage 1, the material is removed remotely. Stage 2, the material is cooled underwater for many years. Stage 3, unused uranium and plutonium are removed at a reprocessing plant. Stage 4, the remaining material is placed in a sealed container and then buried deep underground in a secure location. The material can be turned into glass to ensure there's no leakage in the future, and the material can be stored in the natural environment as long as the landscape is geologically stable. So we can summarise our radioactive waste and safety protocols with the following. Low-level waste is lab equipment and protective clothing. Moderate level or intermediate level waste is containers of radioactive materials and radioactive materials with a low activity, whilst high-level waste is spent fuel rods and fuel rod containers. So for low-level waste, we seal them in metal drums and bury them in large trenches. For moderate level waste, we seal them in drums encased in concrete and stored in special buildings with walls of reinforced concrete. Whilst for high-level waste, we remove them by remote control, store them underwater for 2 or 3 years, any unused uranium and plutonium is removed in a reprocessing plant, and the rest is stored in sealed containers in deep trenches. So if we consider our 3 areas of nuclear safety, well, firstly, we have reactor shielding. So reactor shielding is that when a nuclear reactor is surrounded by thick concrete, it'll act as a shield. This prevents any radiation from escaping and interacting with people around it. You've also got the emergency shutdown procedure in a nuclear reactor. So in an emergency, the nuclear reactor can be shut down by releasing the controls fully into the reactor. This will slow down the fission process as quickly as possible. And finally, you've got handling waste products. So you've got to handle the waste products with great care because it's very hot and very radioactive. So the material is removed from the reactor remotely, placed into cooling ponds to cool, and then is stored in sealed containers until the activity has fallen sufficiently. Now, when we use nuclear power to generate electricity, we've got to weigh up the benefits of nuclear power along with its risks. So what are our benefits of nuclear power? Well, firstly, we can say that there's a lot of nuclear fuel allowing us to use nuclear power for centuries. Most of this fuel can be found in politically friendly and stable countries, unlike gas, coal or oil. Using nuclear power produces less, not none, but less greenhouse gases, so it's better for the environment, and using nuclear power is a very efficient process, so uranium releases much more energy per kilogram than any other fuel. So those are the benefits of using nuclear power. However, what are the risks? Well, the risks are that nuclear reactors have to be designed and built extremely carefully to minimise the risk of a nuclear disaster. The nuclear reactors can be produced and can be used to produce nuclear weapons and can be a target for a terrorist attack. We've got to consider how to deal with the waste produced and make sure it doesn't endanger people or the environment. So we've got both our benefits of nuclear power but also the risks of nuclear power as well. Now, it's important to consider both the risks and the benefits of nuclear power to make an informed decision about whether to use it in the future. Now, nuclear power will never be a risk-free way of generating electricity, but we need to consider how to make it as safe as possible. So to summarise what we've looked at in today's lesson, we should be able to understand the fuel used, the remote handling of fuel, shielding and the emergency shutdown procedure, understand the production, remote handling and the storage of radioactive waste materials, and have an appreciation of the balance between the risks and the benefits in the development of nuclear power. So if we've been successful and learnt in this lesson, we'll be able to explain how fuel rods can be disposed of, describe how radioactive material is removed from a reactor, and explain the balance of risks and benefits in the development of nuclear power. So I hope you've enjoyed this lesson on radioactive waste, which is part of the nuclear physics topic in AQA A-level physics. Thank you very much for watching and have a lovely day.